welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
I am Connie. I am a curious co-host, but I am overwhelmed by the universe, so I'm happy I have my bestie here to explain it to me.
Yay! I'm happy to be here explaining, bestie. I am Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe. And I was thinking about new types of episodes that we could do and a type of long series that we could do every once in a while. And I was looking at, the stack of books that my mother got me for the child I would eventually have back when I was in a real relationship. And and it hit me. What if we do space from A to Z?
Okay. Listen, as the child that I was, I did just read encyclopedias, so this is fine. My grandma worked at Reader's Digest, and so we just had like a couple of different stacks of encyclopedias, and so I would just like skim through them. So, and then I had the Encarta encyclopedias on the CD-ROM. I love those. I think it was Encarta. It had a game. It was like a trivia, like a quiz trivia knowledge game. I want to say it was multiple choice, but like it was like set in a medieval little castle, maybe. I don't remember the details. Maybe you had to like unlock rooms and pass the tests or whatever. And then, but what I learned most from it was the song Greensleeves, because it was the song that they played throughout the entire game. And so I began to learn it well. Just a random piece of
I just
lore.
remember having to learn how to play Greensleeves for band. I have never heard of any of this, and Carta is a completely new term in my brain.
Yeah, it was like a
no, we didn't have
CD-ROM.
CD-ROMs in the woods.
Yeah, that's fair. And as a city kid who was in the laptop program, they were like, "Here, we got to get the students to learn." I got my IBM ThinkPad and my Carta CDs, and I was
so
learning.
Fancy.
Yeah,
but it trained you.
It trained me well,
I guess. So along those lines of space from A to Z, I figured we would obviously start with the A.
Yeah.
And this is really just a way for me to include a lot of miscellaneous astronomy stuff into different episodes, because there are some things like the baryonic acoustic oscillation that we're not going to do a whole, well, maybe we could. But like we're probably not going to do a whole episode about no, we could do one about baryons too. This isn't going very well with these examples, but
That's fine.
There are some things that you don't want to make a whole episode for.
Yes.
Let's just put a bunch of them together. And today we're starting with the A's. Yeah. Yes. Bestie, what astronomy things can you name that start with A?
Okay. Astronomer.
Yeah.
Counts. Is an astrolabe a thing that's...
An astrolabe, yes.
Yeah, okay,
That's
great.
an instrument that can help you determine positions of things on the sky. An astrolabe, yes.
Okay. Accelerator?
Sure. Yeah, we have, an accelerator is a pretty general term, but we have like particle accelerators in physics and stuff.
Getting it from. Let me see. I'm stuck, but I'm happy I had a few. Thrilled.
I did put you on the spot. That's totally fine. Yeah, we could talk about atoms. We could talk about.
Of course.
Now I'm just thinking of all the things that are in the episode. But today we're going to talk about some of those A things. We're going to talk about absolute zero, antimatter, asteroids, and we're going to start by talking about one of many catalogs in astronomy called the Abel catalog. Abel? Abel. Abel catalog.
The Abel catalog, okay.
I've actually never heard this said out loud. I've only seen this written down, I'm realizing, on the mic, and that's okay.
The mark of an academic,
Truly.
Just reading things, right? Reading lots of papers, reading lots of things, and just no one ever actually saying it out loud.
Yeah. It's named after George Abel, who was one of the people putting together this catalog. And it's just there are actually two different Abel catalogs. There's the Abel Planetary Nebulae catalog, and then the Abel Rich Galaxy Clusters catalog. The Planetary Nebulae catalog came first. It's a data set of 86 different objects that were all discovered before 1955 and were thought to be planetary nebulae. Thought being the operative word, because some of them are not planetary nebulae.
Well, dang.
Some of them were galaxies. Some of them were flaws in the photographic plates that they used to take the images. And they were actually like going through the plates by eye and identifying these like fuzzy patches. So they weren't always correct.
Yikes.
Yeah. And then even though all of these were discovered before 1955, the catalog was published in 1966, and it includes classics like Abell 61, which is also known as the Medusa Nebula. It's about 1,500 light years away in the constellation Gemini, which is interesting to me because usually astronomers, the way they like to be clever with mythology is in such a messy, disrespectful way. So I would totally assume and expect them to put the Medusa Nebula in the Perseus constellation, but it's not.
Right. They did like to be messy in that way.
Yeah.
So is Abell 61 just like the naming convention he came up with? And then were they named, was the Medusa Nebula, was that named after this catalog?
That's a good question. Probably, because the reason it's called the Medusa Nebula is because it seems to have these tendrils that come out like Medusa's hair, the snakes that make up Medusa's hair. And we wouldn't have had that clarity until we had telescopes like the Hubble Space Telescope way after 1955.
Right.
And the naming convention for all of these catalogs is that they are the catalog and then the number in the catalog. So he didn't come up with it, but it was just the 61st item in the catalog.
Gotcha. And I was wondering, because I was like, did he just name each thing after himself? But it's because it's just the number of the item in the catalog. Got it.
Right. And remember from our nomenclature episode that the catalog designations are not official names. So these objects will have numbers under different catalogs, and it's just within this data set that 61 applies.
Right.
And then Abell also gave his name to a catalog of rich galaxy clusters. This is an all-sky catalog, so it covers both the northern and southern hemispheres of the celestial sphere. Wow. And it has 4,073 galaxy clusters. Each cluster has at least 30 galaxy members in it.
Okay.
The two parts of the survey were published separately. The northern survey was done first in 1958, and it has most of the clusters, 2,712 of the galaxy clusters. It was taken as part of a survey at the Palomar Observatory in California, and they could see down to a latitude of something like 20 degrees south. So they went through the survey that they had from Palomar and they identified the galaxy clusters. And then they went back in 1989 to do the southern hemisphere, where they used the United Kingdom's Schmidt telescope, which is located in Australia. So they had a nice view of the southern sky. That southern one has 1,361 galaxies in it.
Is that one fewer because of how they counted, or because of, is it less crowded in the southern hemisphere, or that's just how they counted at the time?
If anything, it's more crowded in the southern sky, but not extragalactically necessarily. Just like within our Milky Way, you can see more from the south. It's likely has fewer because they had already gone a little bit down to the southern hemisphere in the first catalog, going down to 20 degrees south. But there were also going to be differences in the telescope. How faint of an object could it see? What was its integration time? Like, all of those differences are going to lead to the catalog being slightly different.
Gotcha.
But once they had collected all of these galaxy clusters, they were able to do some large number statistics on them, which is exciting. Once you get to a point in astronomy where you've found enough individual items of some sort, you can start to do population statistics. And so they were able to establish this system of identifying and classifying galaxy clusters by their shape. The jargon for this is a morphological classification scheme. We do this with galaxies. I think you and I have talked about the Hubble tuning fork before.
I think so, but I don't remember. Exactly.
I've definitely covered it on the pod before, but we broadly separate galaxies into 3 different classes. There's spiral, elliptical,
Right.
and then the irregular galaxies. And that's all based on their shape. And it seems maybe like that's not the best way to distinguish them, but there actually is a lot of physics that goes into what the shape of the galaxy looks like.
Right.
So they did something similar with galaxy clusters, and it's based on how symmetrical they are. If you are less symmetrical, then there's like a different type of gravitational interaction happening between all of the galaxies in the cluster. Yes.
How did they decide what counted as a cluster? Because I'm thinking about how we count continents and like the things where it's like, were they deciding like this area is a cluster? Like, how did they decide what counted as a cluster? I guess.
Yeah. Space is very far apart, so you can by eye determine that lump of galaxies is a cluster.
Okay. I got you now.
Yeah.
Okay.
And these days with huge surveys, you can do this with machine learning where you have mathematical values for how far apart the galaxies are going to be or how large they look on the sky or like in the data set. And then you can analytically or mathematically determine what a galaxy cluster is. But back in the 80s and the 60s, they were doing this by eye.
Right.
And George Abel died in 1983 before they were able to finish the Southern Survey. So they finished it and then published it without him. That's the Abel catalogs.
Gotcha.
There's other catalogs. There's the ARP catalog of peculiar items in the sky.
Not the AARP catalog.
No, just the ARP. And so, yeah, I think we'll probably be talking about a lot of different catalogs as we go through the Space from A to Z series.
Cool.
The next A I want to talk about is absolute zero.
Is Kelvin involved here?
Kelvin is involved here, yeah.
Yeah, so is it 0 Kelvin? But I don't know what the numbers are in Fahrenheit and Celsius.
Yes, it's 0 Kelvin. Absolute zero is the minimum temperature that anything in the universe can have. And it's one of those temperatures that's totally hypothetical because it cannot actually be reached, but we can use it because nothing can actually reach zero energy, at least not until the very end of the universe. So the way we came about imagining that there is a minimum temperature in the first place starts around the 1700s. This is when people are thinking critically and scientifically about temperature and energy and the relationship between them. This is early thermodynamics. As people start to learn more about the relationship between pressure and temperature, there is this idea that there's a minimum temperature because we know there's a minimum pressure. We have the idea of a vacuum where there's no pressure in a space. And since, according to the ideal gas law, pressure and temperature are correlated, they go with each other, then there must also be a minimum temperature.
Oh, okay.
So people start experimenting with this in 1703. A scientist named Guillaume Amontons, probably.
Ooh la la.
Yeah, he establishes his own temperature scale because there isn't a standardized temperature scale at this point. He establishes his own where water freezes at 51 and it boils at 73. And
I notice you're not saying
there's no unit.
There's no unit.
There's no unit.
At 73.
Yes, the value for on his scale for boiling was just 73, and there are no units associated with that. His idea for justifying it, or like the rationale behind this, was that he was looking at the pressure of air, and if you have more pressure, then there's more springiness to the air because it'll like bounce back. It'll push up against something more. So more pressure, more springiness, therefore more temperature, more springiness. And he was imagining what a temperature that would give air zero springiness would be. But he imagined that as a concept, but never tried to calculate it because he knew even then that this absolute minimum temperature could not be reached. So we have to wait another couple decades for Fahrenheit. I don't know, it was like Carl Fahrenheit or whatever the fuck. I don't care. Fahrenheit comes up with the first standardized formal temperature scale. He does this between 1714 and 1724. His name is Daniel Gabriel Fahrenheit, and it's based on mercury thermometers, where mercury expands really quickly with any sort of heat. It's really sensitive to heat. So if it expands and you have it in a graduated cylinder that has markings for its volume, then you can read off that marking, and the volume of the mercury is essentially the proxy for temperature. So that is how the Fahrenheit scale is established. There are markings on a cylinder, and the mercury level when water freezes is at the 32nd marking, and when the water boils, it's at the 212th marking.
Have you used a mercury thermometer before? Because I realize like a lot of people now might not have ever seen one, especially now that we have the little radar guns that we just like point at people's foreheads. But I remember at least once as a child using one. And it's,
I don't know if they would have been mercury still by the time we were kids, because they would have known that was dangerous. But there are, like, the idea still stands of a substance that is sensitive to expanding under temperature.
Yeah, whatever they were using at the time. But I didn't realize that was how it worked. Okay.
Yes. And that is the temperature scale of science for a few decades. And then in the 1740s, in 1742, Anders Celsius suggests a new scale where the freezing and boiling points of water are at more reasonable values. So he puts it's inverted from the current temperature scale. He puts freezing at 100 and boiling at 0. And I'm not totally sure why, but a year later, there's another scientist who comes along, and either independently or just based on, hey, Celsius, you were an idiot for doing that, he flips the order so that freezing is at 0 and boiling is at 100. And that is how we get the Celsius scale, named after Anders Celsius, but originally just called the centigrade temperature scale, and not named Celsius until many years later.
Yes, because 100.
Yes. The next century, in 1848, this is when Lord Kelvin comes into play. Oh,
he's a lord. Oh.
Yes. His name is actually William Thomson, and he is Lord Kelvin of this specific place. And he is one of the fathers of thermodynamics. He uses his position and privilege to devote time to science, and he followed the same logic of pressure being able to go down to 0, so temperature should be able to go down to 0. And he actually mathed it out, and he put that minimum temperature at negative 273 degrees Celsius or negative 460 degrees Fahrenheit, joining the two scales. And that is the temperature where energy, pressure, and entropy, this idea of the universe trending towards chaos or complexity, that all goes to 0 because there is no motion and no change. And the closest we get is the cosmic microwave background, which is at 2.7 Kelvin.
Wow. Okay. Huh.
So that's absolute 0.
Can we not physically measure it, or nothing? Like if it, I guess
nothing reaches it, so we can't measure it.
So we can't measure it.
The next one is going to blow your mind even more, I think. This is Alfvén waves and Alfvén surfaces. There's also Alfvén numbers, Alfvén time, Alfvén speed.
Who was Alfvén?
Alfvén. Who is Alfvén? Hans Alfvén, or Han Alfvén, was a scientist who studied fluid mechanics in a specific context. So let's go back to the states of matter. There's solid, liquid, gas, and then there's this secret fourth thing called plasma. Plasma is when electrons break away from their atoms but stay nearby. So you end up with the negatively charged electrons right next to their positively charged ions that they've just left. And that soup of negative and positive charges is called a plasma. And you usually get them in really high energy or high temperature environments like stars or supernova explosions or around black holes, things that we study in space.
Right.
Plasma tends to behave mostly like a fluid, like liquid or gas. It flows, it can maintain its volume but change its shape But there is this extra layer of complexity because of all of the charged particles. So a plasma actually behaves like a fluid, but with an extra magnetic and electric component. So they have magnetic and electric fields. And the difference between those two, or like one of the most important differences between those two, is that a magnetic field is made of moving charges. So the electrons and the ions moving around, flowing through this space. An electric field is mostly static charges, or charges that are moving between known endpoints, like a starting point and an endpoint, like the wire in any electrical thing you're using. There's the outlet and your computer, for example.
Yeah. I can see those differences in my head. Oh, great.
Okay, good. Yeah, because electric field lines, they have like defined starts and ends, or they're static, whereas magnetic fields, they move in these loops, these giant arching loops.
Electric is Kiki and magnetic is Booba.
Yes.
Booba flows, but electric is sharp. It sparks and jumps and stuff.
I like this. Yes, I approve.
Great. Because I was like, I think it works. Yeah.
Okay, so you have your plasma, and it's moving like a fluid, but it also has this electromagnetic component. In 1942, Hans Alfvén combined the math of fluid mechanics with the math of electromagnetism, and he created essentially this whole new field of magnetohydrodynamics.
I laugh because I just think of the X-Men when you say Magneto.
Fair. He wrote this paper called The Existence of Electromagnetic Hydrodynamic Waves. Over time, that name was simplified to magnetohydrodynamics. And in 1970, he won a Nobel Prize in Physics for that paper. Now we study Alfvén waves and Alfvén surfaces out in space because of how they move plasma. They seem to make plasma wiggle in different ways depending on how the magnetic field is interacting with the plasma. And there are a couple different types of waves. The wave that he initially imagined, we now call them basic waves, which is a little rude.
You know,
that's what we do. These are compressional waves. So the magnetic variations, they're traveling through the plasma via compression in the direction of its motion. So as the plasma is moving, it's like the magnetic waves not snaking up and down. It's like if you are standing in line with a bunch of people and you push forward and then get pushed back. It's like slinkying through.
Pulsing?
Yeah, maybe a pulse.
Okay.
And so they move through the plasma in a certain way that doesn't make the plasma move, but does make it ripple. I have a video for you if you follow this link. It's also included in research notes for patrons. So the video is a simulation of a plasma that's represented by teal lines in a grid. And there are these tiny little yellow dots zinging through the plasma that represent the magnetic field lines and the charged particles moving through it.
Okay.
In this basic wave, you can see that the charges are moving parallel to the wave, and the plasma wave doesn't move much, but it does kind of ripple.
Oh.
It's like if you are in the ocean and a wave comes by, you move up and down, you bob a little bit, but you stay in the same place.
Yeah.
That's kind of like a basic Alfvén wave.
Okay.
You could also have more complex kinetic waves where a magnetic field travels at an angle to the direction of motion for the plasma. And when you have the charges moving at angles, they can get trapped in the troughs, like the valleys of a wave of the plasma. And then they can actually, things can get carried along with the plasma. So if you go into this video, we have that same grid of teal lines that represent the plasma, and the yellow charges, they're moving forward and back. They're moving to the side a little bit, and you can see that it actually makes the whole grid of plasma shift diagonally over time.
Yeah, it's very trippy.
Yeah. So these kinetic waves are they're stronger interference in the plasma. And when we study the motion of the plasma in our telescopes, we can tell what type of Alfvén wave is moving through it, and therefore we can tell the shape of the magnetic field in that space.
Wow.
which is great because, it's hard to study magnetic fields remotely or like the shape of them remotely unless you have another tracer for the magnetic field lines. So the plasma acts as our tracer for the magnetic field lines.
Mm-hmm.
And alpha waves, when they are moving these charged particles along with them, because the charges get trapped in the valleys, they can accelerate the charged particles and heat up the plasma, like in a runaway effect. And this might be a solution to the coronal heating problem, because for a long time we didn't understand why the corona of the sun was like 1,000,000 degrees, which was hotter than the surface of the sun. And it might be because of this kinetic alpha wave accelerating the charged particles and heating them up.
Because the sun is plasma? Or all
Because stars are plasma.
Mm-hmm. Stars are plasma.
Hey friends, it's me. Connie is ordering herself a space and mythology encyclopedia. It's a special edition. She found it online while we were talking. So I figured I'd use this time to share some messages with you. The first message is, of course, a huge thank you to all of the patrons who support us financially every single month. As an independent podcast, it would be so hard to make this show without your support. So thank you, thank you, thank you. I want to give a special shout out and a huge thank you to our Sun-like stars, Scott Reynolds, Tom T, Nicole Bartlett, Ashley Shambo, and Bruce Sedloff. You're golden. You're amazing. You have the perfect amount of mass and gravitational influence, and I'm so grateful for your support. If you would like to help out this indie podcast on Patreon, you would get to hear your name on the show, make it onto the patron star chart, which I just updated after spending a long time trying to figure out how to get Python installed on my new computer. You can also get research notes for most episodes and all of that for $5 a month at patreon.com/palebluepod. If a monthly donation isn't something you're interested in right now or ever, you can make a one-time donation and become a supernova in the Pale Blue Pod sky. That is at the PayPal link in the episode description. And if you can't support us financially at all right now, we totally understand. Times are hard, life is hard, and we want Pale Blue Pod to be one thing in your life that is not hard at all. So if you still want to help us out, you can do that by rating and reviewing us on whatever podcast platform you use, and you can share the episode with someone who you think will enjoy it because word of mouth recommendations are so powerful. But no matter what, thank you so much for listening. Connie and I are honored to be a part of your week. Next, I'd like to recommend another podcast in the Multitude Collective called Tiny Matters. We all know that science shapes every facet of our lives, but so much of its influence is overlooked or buried in the past. Tiny Matters, an award-winning podcast, by the way, is all about tiny things, from molecules to microbes, that have a big and often surprising impact on society. From deadly diseases to forensic toxicology to the search for extraterrestrial life, hosts and former scientists Sam Jones and Deboki Chakravarty embrace the awe and messiness of science, asking questions like, how was IVF invented? What do glaciers tell us about Earth's ancient past? And will humans ever live on Mars? Not if I have anything to say about it. But Tiny Matters is a podcast created by the American Chemical Society, a nonprofit scientific organization based in DC, and new episodes come out every Wednesday, so check them out wherever you listen to podcasts. And before we get back to the episode, an update on merch. We are talking to an artist about designing the blanket, which seems to now be kind of like the big flagship item of the Pale Blue Pod store. So we're working on it, and we are still on track to get you pre-order forms next month. All right, Connie has ordered her encyclopedia. It is arriving on next day shipping from the universe, so that's very exciting. But let's keep talking about the A's of space. The next A on the list is alpha radiation.
Okay.
And maybe you've heard of this?
I don't think so. Currently.
That's totally fine. It is one of, I think we're going to have in each of these A to Z episodes probably a type of radiation. This is the emission and propagation of alpha particles.
Okay.
That's not a useful definition because it kind of uses the term in the definition. Alpha radiation is also produced through the process of alpha decay from radioactive elements, for example, isotopes of uranium, radium, and plutonium. So really, it's like there's this whole class of process that we've just called alpha.
Yeah, I was gonna say, how many lines in the astrophysics dictionary is there alpha? Like, how many pages do we go?
Not actually that many. It's
Okay.
just that this particular process is called alpha, and so all the things associated with this process are also called alpha.
Gotcha.
So alpha decay is a process that produces from one of those radioactive isotopes a more stable daughter particle. I like that they're called daughter particles.
Yeah.
And also an alpha particle. So it's a byproduct of this physical process. An alpha particle is also called a helium-4 nucleus because it is, if you have 2 protons and 2 neutrons and no electrons, that is an alpha particle. It's also a helium-4 nucleus. So a uranium isotope might go down to thorium and an alpha particle, or radium might decay into radon and an alpha particle.
Gotcha. Interesting.
The alpha particle does have a positive charge because there are 2 protons which have positive charge and 2 neutrons which have no charge. But even though they all have that same like +2 positive charge, they have different energies depending on the mass or energy of the particle that they originated from. Because a more massive or a more charged particle is harder to escape from. So the byproduct particle, it's almost like you need more energy. You need to have more energy to escape from that original system. So these alpha particles, they are big and they're heavy because it's 4 little particles all up in there. And so they move fairly slowly compared to other radiation like gamma radiation. And that means they're less dangerous. You can actually stop alpha radiation, most of it with a piece of paper. It won't pass through. But gamma rays will pass right through. And because they're so safe, they're used in a lot of research. They're safe but reactive because they will ionize material around them. So in 1899, alpha particles were used by Ernest Rutherford to help change from the plum pudding atomic model to the model where you have a nucleus surrounded by a cloud of electrons.
Oh, it was a plum pudding before? Like
the one of the earlier models for atoms had the protons and the electrons. I don't even know if they knew about neutrons yet, but probably. But they were all just kind of mixed together.
like in a pudding.
Like in a pudding. Yes. And instead, we now know that they are more ordered so that the nucleus really holds all the protons and neutrons inside, and that most of the atom's space is empty space, but with this cloud of electrons moving around the nucleus.
I'm like, plum pudding specifically.
They were British.
Yeah. I was like,
Yeah.
it just sounded very British.
Like, we're lucky they didn't call it the spotted dick model, honestly. They are used in some cancer therapies because they can react with cancer tissue, but we can really, I think, precisely control the depth of like how far it goes into the tissue. And they're also used in smoke detectors. In some models, the smoke will disrupt the alpha particles that are like in the space, and that sets off the alarm. And in others, the alpha particles generate an electric current that is used to like tell the alarm when to go off.
Yeah, see, physics, I did better in physics than I did in chemistry, but physics has a lot of chemistry.
It does.
Yeah.
We'll discuss this process again with beta particles and beta decay.
Okay, so
in the
next
next
time.
one. Yeah.
Okay, great.
It's a recursive process. We'll loop until you understand.
Okay, great.
The next A I'm talking about is antimatter, and this is an older idea than you might expect. People were kind of jokingly or pseudoscientifically suggesting the idea of negative matter starting in the 1880s, but we have it in the scientific sense starting in 1928 when Paul Dirac, a physicist, was mathematically combining quantum theory and special relativity. Both of these, I think, were fairly young at the time. Special relativity was in 1905. So he was combining these two theories and trying to figure out what happens when electrons are moving near the speed of light, because quantum stuff is really about fundamental, like elementary particles like electrons, and then special relativity is about light and gravity and mass. So electrons moving at the speed of light is the combo of the two. When Dirac was figuring out the solution to this problem, like how to combine the theories, mathematically, the solution ended up being the root of a square. So like he got to the end of the equation and there was a square root involved. And when you take the square of a number, you can have either a negative root or a positive root.
Right.
Like he did that math and then just kind of left it there. In 1930, a couple years later, Oppenheimer.
Oh, that Oppenheimer.
Of the movie, yes, that Oppenheimer.
Of the movie Oppenheimer. I mean, yes. At this point, yes.
He was reading Dirac's paper and interpreted this positive and negative root as a positive and negative electron. So you have an anti-electron, which was then later called the positron. It is an electron. It has the same mass. It's like same on the quantum level, but it has a positive charge. And it kind of opened the door for all types of symmetry in particle physics. So if there's an anti-electron, then all other matter particles must have an antimatter counterpart.
Is that all it is?
Yeah, it's purely to make the math work out, although we have observed them.
Okay.
Yeah.
Because I was thinking about that process you were telling me about that I forgot the name of, but where like something produces a thing, but then it undoes it. Like, I forget what that process was. Something pops into space, and then the opposite cancels it out.
Yes. Oh, okay. You are talking about matter and antimatter annihilation. Yes.
Cool. I'm happy to be in the same school because I really thought I was in a different building. So great.
Yes. So we have observed this. We know that there is now matter and antimatter. So Dirac won the 1933 Nobel Prize in Physics because his math equation was the first to suggest this idea.
Oh.
But in 1932, so like they waited to give Dirac the Nobel Prize until after we had confirmed it. Because in 1932, Carl Anderson detected the positron for the first time with his own particle chamber, like not quite a particle accelerator, I don't think, but a particle chamber that he built on his own. And in the chamber, he would produce some different charged particles, or he would inject charged particles into the chamber. And he surrounded the chamber with very strong magnets. And they are importantly in a circle around so that they would attract the charged particles going all the way around the chamber. So he puts the charged particles in, and then they move around the chamber because they are attracted to the magnets, and the direction that they move in and how tightly they curve around will tell you the charge of them, and whether it's positive or negative, and then how charged they are. And because the charged particles moved in different directions in the magnet, he was able to determine that there are, in fact, positive fundamental particles and negative fundamental particles.
Okay, this is maybe a very basic question, but how is he seeing this? Like, how big is this?
How big is it? It's probably not very big.
Yeah, okay.
Because it's not a particle accelerator, it doesn't need to be huge to let the particles reach up to speed.
But then he sees them with his eyes?
No.
Okay.
They are being detected with instruments.
Okay.
Yeah.
Okay.
Yeah, no, not eyes. They're using something that can detect the electrons when they interact with the material outside the chamber.
Gotcha. Okay.
Or on the edge of the chamber. So we learned that antimatter was real, and we also learned that it's not very abundant in the universe, because if it was, then we wouldn't be here. We know that anytime matter and antimatter are near each other, they annihilate and they cancel each other out. So for some reason, at the very beginning of the universe, there was ever so slightly more matter than antimatter. We call this the matter-antimatter symmetry problem. And we don't know the answer, but it seems like the strategy right now is to look for some mechanism within these elementary particles that like makes them land on matter versus antimatter. The way it was described in what I was reading was that at the quantum state, they can almost be like both at once. They can almost be matter or antimatter at once. And in fact, the particles will oscillate back and forth between matter and antimatter. I think we've seen this. And something happened to make that coin toss land on matter just slightly more often. So like, what was it about the environment early on in the universe or about these elementary particles themselves that tips them towards landing on matter?
Wow. So we're kind of trying to recreate that?
As much as we can. Yeah, recreate those conditions or recreate different types of particles under different conditions. Yeah. So that's antimatter.
Wow.
The next A I want to talk about is the asteroid belt.
Asteroid, an obvious one that I forgot. It's an A space word.
It's a pretty big one.
Yeah.
The dinosaurs certainly think so.
Yeah, they sure do.
And to introduce you to the asteroid belt, I want to take us all back to the 1700s.
Oh.
An astronomer scientist named Johann Bode came up with a law. We call it Bode's law. And it says that if you have a system of objects orbiting some body at the center, then each object that's orbiting should be roughly twice the distance from the central body as the object before it.
Oh.
So if you have like a star at the center and then you have a planet at 1 AU, you should then have the next planet at 2 AU, then 4, then 8. Like it should double. Wow. You kind of see this in our solar system, especially in the inner solar system. Venus is roughly twice the distance from the sun as Mercury. Earth is a little bit too close. Mars is also a little bit too close, but like it does roughly follow that trend. I have an image here for you. And actually one exercise that I've done with people who are learning about astronomy is to teach them the scale of the solar system. And you have them take like a long piece of toilet paper or receipt paper or something, and you have them draw where they think the planets are. If this is the whole solar system, where do you think the planets are? And they always put all the planets like really close together, or they space them out evenly, and their minds are always blown when you have basically what we have them do is fold the paper in half a bunch of times,
right?
Because Uranus is about halfway between the sun and Pluto.
Okay, interesting.
And people think it's going to be like Mars or Jupiter, but it's really not. It's an exponential system. So when we realized that, when Johann Bode realized that, people then started looking at the gaps in our solar system where Johann Bode's law predicted there should be a body. In 1781, William Herschel found Uranus where Bode's law predicted it should be, like at about twice the distance from the sun as Saturn. And then people started looking between Mars and Jupiter because they were like, that gap is suspiciously large. In 1801, Giuseppe Piazzi discovered Ceres, the first major body. It's a dwarf planet now, but it seemed like it could have been a planet then, a full planet. It's about 600 miles across, but they established it as a minor planet, and then they kept finding other minor planets in that same region. Between 1801 and 1845, they found 5 different asteroids, and the 5th was called Astraea, and around that time, people were like, oh, we need a new class of object. Like, these are not little planets. They are a thing all on their own. So they called them asteroids, little rocks from the stars.
Yeah.
Which is so nice.
I love that.
And so now we know that there is a whole belt there. We've named it. There are over 1 million members of the asteroid belt. Wow. They range from 30 feet across to 330 miles across. That's the biggest asteroid. It's Vesta. It's, after Ceres, because Ceres is technically a dwarf planet now. The total mass of the asteroid belt is about 3% the mass of the moon. Oh. It's very small.
Because so many things are so small.
Yes.
Wow.
Yes. So many things are so small. The belt is about 1 astronomical unit thick. That's the distance between Earth and the sun. So it goes from 2.2 astronomical units to 3.2. So like right between Mars and Jupiter.
Wow. She's a thick one. Interesting. We cataloged everything in the asteroid belt. I imagine things keep being added to the asteroid belt because they're little rocks from space.
Yes. And little rocks combine, little rocks break up.
Yeah.
Sometimes little rocks come in outside the orbit of Pluto. There is a whole other bigger kind of asteroid belt called the Oort cloud. And things can fly in from the Oort cloud. They can interact with the asteroid belt for sure. So yeah, it's pretty dynamic. But we are monitoring it. The Center for Near-Earth Object Studies monitors asteroids for potential impact. So they constantly have a list of any asteroid that could potentially come within like a few thousand kilometers of us.
And they report on every single one of them because there's always an article that we're almost going to get hit by something, and a bunch of people hope that we do.
That, I think, is a more recent development.
Yeah, I think so.
Yes, they are monitoring them. When it comes to the bigger asteroids, we can predict their motion better. So we'll have more of a warning for the bigger ones than the smaller ones, but that's okay because the smaller ones can break up in our atmosphere and won't be that damaging. But we are actively monitoring anything that comes within 4.6 million miles of our orbital path.
Wow.
And that's the entire orbital path, not just the part of the path that the Earth is on at that moment. So when people say that there's like a 3% chance of collision, that's usually collision with our orbit, not necessarily collision with the Earth. And because it is not CNEOS, it is not the Center for Near-Earth Object Studies that puts out those, this is going to hit us with a 2% likelihood. It's journalists who are looking through their site and are like taking these likelihoods.
I may have
and then
been
running
one of
with
those, Used to be my job.
Yeah.
And try to tell people about science, and maybe you get some of the science wrong.
You're right. Yeah,
or
look,
over-exaggerate it because you work at a tabloid newspaper. It's fine.
But also, scientists aren't the most clear with what their data sets actually are showing.
Yes.
So I can understand the confusion. And then in addition to CNEOS, NASA has its own Planetary Defense Coordination Office that coordinates with the government. And NEOWISE is a telescope that scans the sky in infrared to detect cool objects and cool threats. So we have a telescope up there it's sweeping the whole sky. We have a planetary defense group and this I think nerdier CNEOS group that is like monitoring everything. So we're good.
Yeah. We'll
I'm not
know.
worried about asteroids.
We'll know.
Mm-hmm. And then the final A I want to talk about is the A-type stars. This is a whole spectral class of stars. It's the third most massive spectral class of stars after O and B type stars. And they are like just a step above the sun. They have a mass range between like 1.6 and 2.3 solar masses, which is pretty narrow. Their temperature ranges between about 7,500 and 10,000 Kelvin. It's a bunch of degrees Fahrenheit. It's a lot. And they are between 10 and 40 times the brightness, the luminosity of our sun.
Wait, is the sun an A-type star?
The sun is a G-type star.
Oh. Is the scale in order of the alphabet?
No.
Okay, great.
I know. It goes from most massive to least massive. O, B, A, F, G, K, M. There's like historical reason for why, but it is just like an artifact of an old system that we have just lived with. We've just kept it.
Is it related to Greek?
No.
So it's not alpha, beta, omega type stars? Okay, great.
Damn, that's good.
Yeah, I was curious.
But it's OBA, like omega. Mm-hmm. Yeah. But if this seems like a very small mass range to you for this entire spectral class of stars, it is. But in that mass range, you get a very interesting internal structure. These A-type stars are the first of the spectral classes to be fully radiative. So if you have lower mass stars like M, K, G, F, they have convection and radiation happen. Actually, the M-type stars are mostly fully convection. But then you have a bunch of stars that are a mix of radiation and convection, which are both ways that you can transport heat from the center to the surface of the star. Convection is like when water is boiling. It's heat transfer through actual, like...
movement?
For movement, yes, thank you. And then radiation is when the heat is transferred by just like moving through the medium and not churning. There's like a unidirectional motion
Like
instead
an
of
oven.
a cyclic motion,
Like an oven?
but not a convection oven.
Not a convection oven.
Right. Just the regular
The
old...
regular oven. Because the
Yeah.
convection oven has some sort of like air and pressure, right?
I don't know exactly how it works, but yeah, and some of them have magnets, or maybe that's an induction oven. I don't really know.
Yeah. No, you do space, not cooking.
Oh, I do cooking.
You do
but
do
not,
some
but
cooking.
not the mechanics of cooking.
Yeah, not the mechanics.
Yeah. So the A-type star is the first that's fully radiative. And without convection, you don't have the mixing of the plasma inside the star. So you don't get as much motion of charged particles, which means you have weaker magnetic fields, weaker stellar winds, and lower X-ray emission than you do for the lower mass stars and some of the higher mass stars. Because the higher mass stars can generate magnetic fields through, like, just they have enough energy and like heat going on, and A-type stars are in this kind of middle zone. They live for around 2 billion years, so maybe 20% the total lifespan of our sun eventually, and they are not massive enough to go supernova. So they will most likely puff up into like a supergiant phase. They will shed their outer layers and then eventually become a white dwarf. Some notable A-type stars are Vega, which will one day be our North Star. Altair, the two of them are 2/3 of the Summer Triangle, and they are wrapped up in a Chinese myth that I love about a cowherd and a weaving maid who fall in love, and they are not supposed to be together.
Star-crossed? It's star-crossed?
It's literally star-crossed. And the cross comes in because the weaving maid works for the like divine empress who doesn't want her to be with the cowherd. So she separates them by creating the stream of the Milky Way. She turns them into stars. The weaving maid becomes Vega. The cowherd becomes Altair. And the empress creates the path, the stream of the Milky Way, the Silver River, as they call it, to separate them. And there's one day a year when a flock of magpies acts as a bridge across the river so that they can meet, and that is the Qixi Festival, which happens on the 7th night of the 7th lunar month. That's when they can be lovers, which is very nice.
And what does that mean in the sky? Like do they actually get to touch, or like?
No, that's just the myth ad. But
okay. I was like, is there a reason why? Like, at this time of year, like they've moved enough to be in the place where they get to touch. And I was like, oh no.
They don't move, but there is another nearby star called Deneb that I think is like the magpie in the story. And so the three make a triangle. They're called the Summer Triangle. And I think maybe Deneb appears to be like more in the stream of the Milky Way, where Vega and Altair are clearly on either side of it. So maybe that's how it starts.
I'm gonna look for that in my Skyview app when I
please do
stargaze next.
Yes. And then another famous A-type star is Sirius A, which is the brightest star in our sky. And that doesn't mean it's intrinsically the brightest, because A-type stars are not the brightest, but it's so close to us, only about 10 light years away, that Sirius A looks really bright and is wrapped up in a lot of mythology, as we discussed in the episode a few weeks ago.
We did. Have we seen an A-type star transform? Like go into what you said it would?
Yeah. We've observed these at all the phases of their evolutionary cycle, because their lives are so short. They're not like M-type stars that take trillion years to go through all of their fuel. So our idea of an M-type star's eventual end is all based on models. We have real examples of A-type stars that have stopped fusing in their course.
Gotcha. Okay, cool.
So that is, I think, as much A as I can fit into this episode.
Sounds good. That's about good. Yeah. Uh-huh.
Yeah.
I'm sure there are so many more.
So many more. And maybe after we get to Z, we'll come back.
Yeah. Are there AA words? Aardvark.
Are there space aardvarks? Yeah, that was. I'm sure there's like a Dutch person who has an astronomy thing named after them.
Exactly.
Yeah.
I learned so much. I was excited to see. Oh, so wait. I am confused about something. So Sirius A is an A-type star, but the A is actually just the designation that it's the bigger star in. It's the main star in its galaxy system.
Yeah, or not the main star, but the first star that we discovered because it's the main star. Yeah, so we know that Sirius A has at least one companion star, a white dwarf that we call Sirius B.
Right.
But there might be other companions that we haven't found them yet, but we call it A just because it was the first one found.
Gotcha. Okay. But
Great
there
question.
can be the star A in M-type stars or whatever other type stars.
Yes. My favorite system of planets is the Kepler 186 system, and Kepler 186a is an M-type star.
Ah, okay. Thank you. Look at
Thank
that.
you for asking.
Yeah.
I love this.
Yeah, this was good. It hit my encyclopedia deep dive, inner love. So this was fun.
Amazing. We will do the B episode in a month or whatever, in some weeks. So between now and then, let us know what B things in astronomy you want us to cover.
Yes, please let us know. So I can learn some new B space words.
Yes.
Even if your name doesn't start with A, you're space.
Because neither of our names start with A, and
we're
we are space.
Exactly. Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.